So here we talk about the relativity of length. So the length L0 of an object measured in the rest reference frame of the object is proper length. Similar to the time, when you measure in the rest frame, is called the proper time. And here is called the proper length or the rest length. So measure of the length from any reference frame that is in relative motion parallel to that length, are always less than the proper length. Always less than the proper length. Okay. So if the relative speed between frame is v, the contracted length L, and the proper length L0 are related by L equals to L0 multiplied by this factor, square root of 1 minus beta squared. Beta is V over C, if you still remember. Okay, so this is actually 1 over gamma. Gamma is 1 over square root of this term. Okay, so as I mentioned yesterday, gamma is always larger or equal to 1. So L is always smaller or equal to L0, the proper length. Okay, so does a moving object really shrink? Reality is based on observation and measurement. If the results are always consistent, if no error is determined, then what is observed and measured is real. In that sense, the object does shrink. However, a more precise statement is that the object is really measured to shrink. Motion and factor measured, and thus reality. Okay. So how do we understand this relativity of length? So actually you can just look at a simple equation like L equals C times T, delta T. L equals C times delta T. Yeah, in the past we will consider that T is absolute. T should be the same for all the inertial reference frame. Time for me, for you, and for other planets should be the same. But actually not. If the frame is moving, then there will be time dilation. The time becomes longer. Yeah, the time becomes slower. And yeah, at the same time, if you don't consider the time dilation, then the other way around would be the length contraction. This one becomes shorter. It feels like something strange, but no matter the time dilation or the length contraction, it is still to we have the universe speed of light for difference in inertial reference frame. Okay, so let's take a look at the example problem. So it says Sally at point A here. Sally is point A here, or point A here, and Sam's spaceship of proper length L0. Suppose it does not move, and then you measure the length between B and C. Then this is the proper length, 230 meters. Pass each other with constant relative speed. So actually this spaceship is moving to the right side in the velocity v. Yeah. So Sally measured a time interval of 3.57 millisecond, which means that it's just like there is a sensor here to detect. So when the front of the starship comes to here, then it starts to count the time. Then the starship is still moving to the right side, and then until the sensor detect the tail of the starship, of the spaceship, then it stops, and then it feels that because when we need to measure the length, we need to use the time to measure the length, because the only constant is the speed of light. So we use the time interval to measure the length of the starship. So for the ship to pass her from passage of the point B, in terms of C, what is the relative speed V between Sally and the ship? Okay, so here, here V should be L over delta T, L over delta T. And actually this length is due to the length contraction because originally this is a proper length. But in Sally's reference frame, this spaceship is moving. So the length of the spaceship will contract in Sally's reference frame. So this L should be L0 over gamma. So the contracted length. And the delta T will be the proper time because the time is at the point of Sally. So the clock doesn't move. She only used a clock to measure this 3.57 milliseconds. So this is proper time though, doesn't matter. Okay, so actually this is L0 square root of 1 minus V over C quantity square over delta T. Okay, so we can just move this term over, and then take the square on both sides. So we have a V delta T over L0 quantity square equals 1 minus V over C quantity square. Like this. Okay, so we can try to gather these two terms together, then we can find V. So we can move this term over and then factor out V. So we have a V square and then delta T square over L0 square and then plus 1 over C square, like this, equals 1. So finally, we can just move this term over and then take the square root on both sides. So we have a V equals 1 over square root of L0 square C square, and then here we have a C square delta T square plus L0 square. So it becomes L0C over square root of C delta T square and then plus L0 square, like this. And then we can plug in the values. So L0 is 230 meter, 230, and then times C, because it said in terms of C, we don't need to plug in 2.998 times 10 to the 8th power. And then take the square root, and then, yeah, actually we can plug in the value here. So we have a, let's see, yeah. So we have a 2.998 times 10 to the 8th power, and then times delta T is 3.57 times 10 to the minus 6 power, and then quantity square plus 230 square. So this value will be 0.210 C. So which is around 1/5 of the speed of light. And actually, if you just follow the classical mechanics, you just substitute V equals L0 over delta T, which will be a similar value. So this is 230 over 3.57 times 10 to the minus 6 power. Let me just calculate. So 230 divided by 3.57. Let me see. So this V will be will be 6.4 times 10 to the seventh power. So it will be divided by 2.998. So this is around 0.215 C. So this is quite similar, because when you consider gamma for beta equals 0.210, for this case we have a 1 over square root of 1 minus 0.210 squared. So this value is nothing but 0.978. So if you just follow the classical mechanics or classical physics, then the error will be like 2.2%, which is not so great. So which will be acceptable for most of the cases, but maybe for positioning, then it may not be good enough. Okay, so yeah. Okay, so here we have another sample problem. So this one says, caught by surprise near a supernova, 就是超新星哦，超新星。So you race away from the explosion in your spaceship, hoping to outrun the high-speed material eject towards you. 就是说超新星啊，它会爆发嘛，就是一些行星它死掉之后啊，它就是一直塌缩到某个程度，它就会爆发嘛。那就是超新星爆发那 So you race away from the explosion in your spaceship. 那你希望就是你不要被那些爆发时候啊所产生的那些高速的物质被喷到嘛。So your Lorentz factor gamma relative to the inertial reference frame of the local star is 22.4. So this is actually the gamma. This is the gamma. So to reach a safe distance, you figure you need to cover 9 times 10 to the 16 meter as measured in the reference frame of the local star. How long will the flight take as measured in that reference frame? So actually you move very fast. You should move very fast to escape. Okay, so let's check what is the speed of u at when gamma is at 22.4. So we have a 22.4 equals 1 over square root of 1 minus v over c quantity square. So this is gamma. Okay. So actually we can do some algebraic calculation. You move this term over, take the square on both sides, and then you do something simple things. Then you will see that v equals 0.999 c. Okay. 0.999. 99.9% of the speed of light to escape. Okay, so in that case, delta t, which is the time to escape in that reference frame. This is actually this is actually the rest frame, which means the proper length. This is the proper length, and then this is the time in that reference frame. So it will be 9.00 times 10 to the 16 power, and then divided by 0.999 times 2.998 times 10 to the 8th power. So this is the speed of light. This is the speed of light. This is the contracted length. This is the contracted length. Actually, this is the this is the L over C equals L0 over gamma. Over gamma over C, like this. So this one is here. This is the contracted length. This is the speed of light. Contracted length over the speed of light will be the time in that reference frame. Okay, so in that case, this value will be 3 times 10 to the 8th second. Which is around 9.52 years. 9.52 years. So, sorry, this is the proper time. This is the proper time. This is the proper time. Because so you figure you need to cover. So this is not this is the proper. This is the proper time. This is the proper. No. This is the proper time. This is the proper time. And actually, so in that reference frame, so question B is how long does the trip take according to you? So actually, this is the. This is the time it takes to measure how long you run a race. So this is not the proper time. This is the time measured on the star. And then how long does that trip take according to you? Because you are moving. So in that case, delta T0 will be delta T over gamma. So it will be 9.52 over 22.4, which is 0.425 year. 0.425 year. Actually, because you are measuring the time. That you are travel. So it's just like the twin paradox. When you move very fast, your time runs slower. Because your time is delayed. So you only pass through 0.425 year. However, on the star, it feels like you pass through 9 years. So actually, the relativity, even though the special relativity is some sort of mind bending. Even though the calculation is not difficult, you don't need calculus. You only need to multiply, divide by something. But how do you determine whether you need to multiply something or divide something is somehow difficult. So next we will cover the Laurent transformation. The Laurent transformation equation related to the space-time coordinate of a single event seen by our observer in two inertial reference frames. S and S prime, where S prime is moving relative to S with velocity v in the position x and x prime direction. The four coordinates are related by this equation. So compare with the Galilean transformation. It will be like we don't really have this gamma factor. Because for the classical mechanics or the classical physics, if this is the reference frame suppose this is the reference, and then another reference frame, this is moving to the right side with velocity v. Then suppose a point here. Suppose you consider a point here. For this reference frame S, the x-axis is x, and the time will be shared by both coordinates. So t and t prime will be actually the same. So for Galilean coordinate, then it will be like x prime equals x minus vt, t prime equals t. Both time coordinate will be the same. And then here, because this axis is moving to the right side with vt, so this part will be x prime minus vt will be this x minus vt will be this x prime, like this. So this is a Galilean transformation. But actually this is not true for general case. If you move very slow, then if you don't consider this gamma, will be fine. Just mention, even though the speed v is as large as 1/5 of the speed of light, then if you don't consider the gamma factor, the error is only 2.2%. But yeah, in our daily life, our speed must be much less than the 1/5 of speed of light. So without considering gamma, it doesn't really matter. But actually, we need to consider gamma when the speed is fast. Actually, if you substitute this, if you use this Galilean transformation to substitute into the wave equation we just described in the last chapter, then you will be wrong. Actually, you need to use the Laurent transformation and then you substitute into the wave equation, then the form will remain the same. So here, I will not try to tell you why it will look like that, but actually it needs some mathematics behind to really find out why there is a factor here, why there is a factor here, and why is the time is different by this term. Okay, now of course we suppose the velocity is parallel to x-axis, so there is nothing changed to the y and z axis. Of course you can also move in the y and z axis, but just make things easy, you can just assume our x-axis is parallel to the velocity. Okay, so here we have a gamma factor here, and then we also have a gamma factor here, but we also need to subtract this term. So these two coordinates will have a different time axis because there will be time dilation. And if you change back from s prime to s, you still need to multiply by gamma rather than divided by gamma. It is very strange but interesting fact. If you don't believe, you can try to substitute again. So for the first step, you can just try. Here we have s, and then we have s prime, and then for the second step, you can regard s to be the s double prime, and then you do this again, and then here we have all the prime, x prime, y prime, z prime, and then t prime, x prime here, and then the left side become x double prime and t double prime, and then you substitute again, and then you'll find that x double prime and t double prime will be the same as the x and t. So which means that when you change from s to s prime, and then you need to multiply by this gamma factor, and then you change back, you still need to multiply another gamma, but it turns out to be cancelled. It is very interesting. Okay, so this is the Laurent transformation we will use to consider the coordinate change between two inertial reference frame. Okay, so yeah, so this is the other way. So if you just transfer it back to the original axis, because the v, when you are in s coordinate, this one of course move to the right side, so you need to subtract the v, and then if you are in the s prime coordinate and then you change back to s, this one is moving to the left side in velocity v. So here we have a plus rather than a minus, but still we need to multiply by this gamma to make things correct. So this is the interesting part for the Laurent transformation. Okay, so this Laurent transformation has a very interesting property, which means that in relativity, we still need to keep something to be constant, which means that this is so-called we will sometimes define it as S to be this term. For this term is for the S coordinate. This one is for the S prime coordinate. Then we just substitute the time, the coordinate, the space coordinate here. Actually, this is a 4-vector of space-time rather than these 3 coordinate space. This is time. Actually, this is a 4-vector for the space-time coordinate. And then we substitute this t and xyz into here, and then we also substitute t prime, x prime, y prime, z prime here for the s prime coordinate. Then they must be the same. In theory, we call it invariant. Actually, in sigma system, I suppose you learn a term called the invariant, right? Time invariant, linear time invariant, LTI system, something like that. So 这个中文就叫做不变嘛，不变量。So in relativity, we need to keep this S to be an invariant variable, which means that if you consider this value in one coordinate S, and then consider in another inertial reference frame S prime, they must be the same. So let's see why it's like that. So now we already know that y equals y prime and z equals z prime, as shown in here. So we can quickly see that this one and this one will cancel. This one and this one will cancel. So we just keep out those 2 terms. So we only consider is c squared t squared minus x squared and c squared t prime squared minus x prime squared. Okay, so now we can plug in these 2 equations here. So we have t prime equals gamma times t minus vx over c squared, and then also we have x prime equals gamma times x minus vt. Okay, so so let's just plug in this one into here and then this one into here. So we have a c squared t prime square minus x prime square. Okay, so now we have this one. We have a gamma square c square, and then t minus vx over c square, quantity square. And then the second term will be this one, gamma square x minus vt quantity square. Okay, so here gamma square can be factored out. So we have a gamma square, and then we here have a square here. So this is t square minus a minus b square will be a square minus 2ab plus b square. So we have a c square t square minus 2 times this one, 2 times this one times this one. So we have c squared here, c squared here, we cancel. So we have a 2tvx. And then we have here we have c to the 4th power, partly cancel with this one. We have a v squared x squared over c squared. Okay. And then we subtract this square, will be minus x squared plus 2xvt, and then subtract minus v squared t squared. Okay, so we can see that this is minus 2tvx, this is 2xvt, so they are the same with opposite sign, so they cancel each other. And then we can do some factorization. So first of all, we have a c squared t squared here, and then also we have a v squared t squared here, so that we can factor our t squared. So we have a c squared minus v squared multiplied by t squared, and then plus this one. We have a common factor of x squared, so we have a x. Maybe we can also factor out 1 over c squared. So it becomes something like minus x squared over c squared. Okay, so this one becomes c squared. This one becomes minus v squared, like this. Okay, so we have a common factor c squared minus v squared here. So we have gamma squared, and then we have the common factor c squared minus v squared. So we have c squared minus v squared. And then here we have a t squared minus x squared over c squared, like this. And then if you still remember, gamma is 1 over square root of 1 minus v squared over c squared. So taking square on both sides, we have a gamma squared. And then here we have c squared minus v squared, and then c squared on top, like this. So here we have c squared over c squared minus v squared multiplied by c squared minus v squared, and then we have a t squared minus x squared over c squared. Okay, so this one and this one can cancel, and then we can distribute this one here, so it becomes c squared t squared minus x squared. Okay, so we show the so-called invariant for this s variable. And then here we can clearly see that the relationship between the time dilation and the length contraction, because this one must be a constant, so that there must be something like this one become smaller, or this one become larger, or either this one becomes smaller. So it refers, the left one refer to the time dilation, and the later one refer to the length contraction. So this one becomes larger, or this one becomes smaller, will make things balance. Okay. So, okay, so let's take a 10 minutes break.